Hello friends, welcome to this annual refresher program in teaching. It's called ARPIT, course on advances in agricultural engineering. So I am Dr. Mailapalli. I'm an associate professor in agriculture and food engineering department, IIT Kharagpur. So in this lecture, what we're going to learn is first we're going to talk about irrigation application methods, and then the irrigation efficiencies, uniformities, and then so what in terms of the efficiencies with respect to the yield. So we're going to see all these four aspects in this lecture. So the first thing is the water application methods. So if you see this is the broad classification. So one is the based on energy and pressure required. So it could be classified into as a gravity. So it doesn't require any energy. So with the simple the gravitational force, the water can be conveyed to the fields. For example, border irrigation, basin irrigation, furrow irrigation, these are the surface irrigation methods. So and then the next category is pressurized irrigation. So water needs to be pressurized and pumped to the for these irrigation systems such as drip irrigation and sprinkler irrigation systems. The other category is the placement of irrigation water. So one is whether you are applying it on surface, soil surface, or in subsurface, or the overhead. So based on the placement of irrigation water, so these are classified, and and again the surface, if you are applying water in surface, there is a surface irrigation, border irrigation, basin, and furrow, right? Even drip also, you are applying water on surface or near to the surface. Whereas subsurface, so water will be applied beneath the ground nearer to the crop root zone. Whereas overhead irrigation, so the water system, the applicators are above the soil surface, and then from there it is going to apply to the field. So it's like overhead sprinkler or hand watering, so all comes under this overhead classification. And then the last one is it is based on the wetted area of crop root zone by irrigation. Okay, so when you apply water on the surface, and if you after the irrigation, if you make a cross section, and if you see the soil moisture the pattern, so based on that particular shape, the application is classified as flood irrigation. So the floods are mostly the rectangular pattern or soil moisture pattern you get, because the water is applied throughout the field at the same time. So then there is a basin irrigation, furrow irrigation. If you see this, and the drip irrigation, you see, so look at here. So this is a rectangular type of irrigation. So mostly the sprinkler irrigation, because water is applied to the field at the same time, just like your rainfall. And the subsurface drip, so what if suppose the dripper is there somewhere here within the soil. So this is within the soil, so it forms a bulb shaped wetting pattern. And then the furrow, there is a furrow irrigation. So water will be applied through the channels, so then the water will be infiltrated through the surface as well as through the bottom. So it forms a bulb, but it's not exactly like a circular, but half I mean 3/4 circular. There is a subsurface drip where the dripper is placed within the soil. So you can clearly see the egg-shaped water pattern here. So this is the way the irrigation methods are classified. One is based on energy requirement, other one is placement of irrigator, and then wetted area once you applied the water in the surface. So then the so next is you have surface irrigation methods. Let's focus on one by one. One is the borders, that is surface irrigation. So this is the best adopted, sorry, this is the best adopted for the close growing crops such as alfalfa crops and the grass crops, and this is suited to standing water. Okay, and then this is suitable for loamy to heavy soils because this is required, otherwise what happened, the amount of water you applied, that will infiltrate very fast way. So the soil should be heavy soils like near to the clay soils or loamy soils, and it's good for flat or small slopes. So mostly we expect the fields are leveled on the flat slopes, and the typical efficiencies range from 70 to 85%. So this is a well developed or well designed system can achieve up to 70 to 85%, and no energy is required because the gravity flow is sufficient. Gravity water will be conveyed to the field channels or field through gravity flow. So it has the three types. The first one is level borders, the almost the flat slopes we expect here. Basically the pots are like initially there is a floodgate through which water will be input to the system, and there is a border strip, so water will be conveyed, and there is a levees, so which separates the borders. Okay, so then there is a graded border. So the graded border will have a mild slope. So from to transport water from head ditch to the tail ditch, and there is a contour levees. So the levees are planned or designed on the contours. Contours are the equal elevated the elevation points. So this is the strip. Okay, so then this is the head ditch and this is the floodgate, so through which the water will be conveyed. And then so the next is you have the basins. So the basins can go up to 400 meters, so or 15 hectares of the area. So the basically this is best adopted for close growing crops and also suited to the standing water, similar to your border case. So this is also useful for alfalfa crops and other grass crops, and loam to heavy soils similar to the border irrigation. A good flat and nearly level ground is required. Typical efficiencies are 80 to 90% will achieve if the system is or the irrigation system is developed or designed very well. No energy requirement, similar in case of border irrigation. So it has, suppose this is the plant 1 and plant 2. So the borders, these are the basins and supply channel. So the water will be moved from supply channel to the border, basin. So here also another basin. So this is most suitable for this paddy cultivation or the horticulture crops. So then the next is the furrow irrigation. In furrow irrigation, also this is best suitable for widely spaced crops and mostly row crops, and then suitable for loam to heavy soils, and good for flat and small slopes. If you have, it requires some slope because the furrow irrigation consists of different channels, like the field is divided into different channels, fields like open channels, and the water will be conveyed through the channels. So it will be like this, and water will be slowly infiltrating into the field, and the plant will be sometimes on the beds. Okay, so the plants will uptake the water from the furrow to from furrows actually. So, as previous case, no energy is required because the gravity is, I mean, flow. This is the gravity flow. So, the level furrows, the name indicates, so it's less slope or mild slope or zero slope, the flat slopes. So, it has, this is the head pipeline, and sometimes we also have the field channel here, and these are the furrows. So, the individual channels are the furrows, and graded furrow will have the slopes or the less slopes, and then contour furrows, similar in case of borders, the contour borders, the contour furrows. So, the field channels follow the contours, or similarly the and the beds follows the contours. So, here the plants will be grown over here. So, these are the siphons. So, as I mentioned here, instead of gate, instead of pipe, we also have a field channel here. So, this is the field channel, and from field channels we use the siphons to convey water from the field channels to the field. Okay. So, the next is the sprinkler irrigation. So, the sprinkler irrigation basically it has as a setup which consists of the main line. This is the main line through which all the laterals are going to follow from the main line. On each lateral there will be the riser pipe. So, each riser pipe will have a sprinkler head on top. So, this is the riser pipe and sprinkler head. So, to the sprinkler head we are going to spray water to the soil surface. So, the main important thing here is, so this is pressurized system. So, we need to monitor the water through the water meter, and mostly this is suitable for the any kind of crop, like wheat crop and maize crops, all the things. And basically the sprinkler head will have different kind of sprinklers. So, for example, here the 2 nozzle bronze impact sprinkler clearly showing. So, the impact sprinkler has the impact arm here, and then there is a spread nozzle, and this side there is a range nozzle, which is I mean this is a trajectory angle, and this is the bearing, and this is the spring. So, it's basically what happens if you see similar kind of the system I have with me. Okay. So, if you look at here, so this one, so this particular thing is the range nozzle. Okay. So, then this is the impact arm. So, what happens when the water moves and hits this one, okay, so this arm, so this is going to move, but because there is a counterweight here, so this is going to come back here. Okay. So, when the water jet hits this, it is going to move, and because it is a spring, and it is going to go back. So, it is like one by one, right, 1 2 3. So, it goes. Similarly, since it is a moving head, so for each impact it is going to move. So, it is going to move like this. Okay. So, it's both ways. One is I mean the nozzle is going to split, sorry, the arm is going to split the nozzle, and at the same time, so this is basically the counterweight which brings the back, and the spring and counterweight helps in bring the arm back, and with that impact the whole head is going to move slowly. So, this is the mechanism, and then you have so in the sprinkler irrigation, this is the best adapted for short crops and suitable for sandy soils. Okay. So, why it is suitable for sandy soils? Because the water which is sprayed on top of the surface, so should not be ponded on the surface. So, this should move as fast as possible to meet the crop water requirement, and good for all categories, category of soils, and typical efficiencies range from 85 to 95% if the system is well designed. Of course, energy is required because the water needs to be pumped through the system, so the energy is required in this case. So, if you see here, this is the spray pad sprinkler. This is another kind of spray sprinklers. So, the nozzles are here on top, and then when the water is going to hit this pad, and it's going to flash up like this, right? It's going to sprinkle that. So, this is one kind. Then there is other kind also available here. So, smooth, this is the deflector pads basically. These are the deflector pads. Okay. And then so the next is you have the sprinkler irrigation types. If you see, there are a number of types available. One is LIPA irrigation system, that is a low energy precise applicator, which was developed in the United States in 1980. So, in the conventional case, what happens, so the riser pipe is high and then there is a lot of drift, and in order to save that drift, so this low energy precise applicator has been designed. So, with this, so this is only 8 to 18 inch from above the ground, and you can save up to 20% of drift, I mean water due to drift. So, that is because even the sprinklers also, the low energy sprinklers, low pressure sprinklers, so it can save the water which is lost through drift in case of LIPA. So, then the solid set and permanent sprinkler. So, in the fields, the during the crop period, the sprinklers are set up, they will be there in the field throughout the season. So, this solid set, we cannot move this system. There is a travel gun system. So, this will irrigate to the entire field. So, it will be moving from one end to other end, and this is the gun, this high pressure gun. So, that will be used to water the plants. So, whatever the drift you are getting here, so that is going to fall down, which covers the nearer plants. And then there is the side roll system. So, in the side roll system, the sprinklers are on the axle, then the whole in the system will be moving from one field end to other field end and irrigating the field simultaneously. Okay. Then the center pivot or linear move system and the linear move system. So, in this case, the field will be watered in a circular fashion. So, initially, so this is the starting point, the old central pivot system. So, this will be moving from one, the whole circle will be finished, and then the entire unit will be moved to another nearest spot, another circle will be completed. So, if you see this, the irrigation will be applied in circular shape here. And there is a portable or hand move sprinkler system. So, this is the manual. So, once the part of the field is irrigated, so the whole system will be, the laters will be moved to the next spot and irrigate. Okay, so, these different kind of sprinkler systems. And then the next is the drip irrigation system. So, it is also called the micro irrigation system. So, this is most suitable for high density orchards, the tree crops and high value horticulture crops, and suitable for sandy soils similar to in case of sprinklers, and infiltration rates should be moderate to high, and the typical efficiency could range up to 85 to 95%. Of course, this requires energy. So, if you see this system, the system is similar, the components, most of the components are similar in case of sprinkler system, but the main important thing is the filtration unit here. So, the filtration unit, this is the source, the water will be taken from the the source, then it passes through the hydrocyclone filter which separates all sand particles, and then move to the sand filter which removes the even the finer particles, and then there is a screen filter which removes even finer particles, and then the clean water moves into the system. So this is the main, and then these are the sub mains or the laterals, and on each lateral there will be a dripper. So the dripper will slowly drips water at a particular plant, and only it waters the particular plant. It doesn't water, the entire the field. So this way you can save a lot of water, and you can achieve up to 95% irrigation efficiencies. Okay, so this is the drip irrigation system. And then so the next is the type of drip systems. If you see, so there are basically two main types. One is online emitter or online emitter system. So there is a drip tape. So the drippers will be attached externally to the drip tape or lateral line. The drippers are fixed externally on the laterals, and dripper space can be adjusted. So it's like you can take these drippers out from the lateral. So if you see here, this is one dripper. So it has like the small tiny burp we call. This is called a burp. So the burp will be inserted into the lateral, and this is the outlet point. Okay, so if you open this, and there are the different components. So I cannot. Maybe I'll try the other one. Okay, fine. So this is the kind of but all the drippers are in different colors. Look at this here. One is black color dripper and blue color dripper, and then there is a yellow color dripper. So if you see in the presentation, so each dripper will indicates for different flow rates. Okay, so look here. So if you see here, this is the black one, that's a 2 liter per hour, and then there's a blue one 4 liter per hour, and yellow one 8 liter per hour, and the green one also 8 liter per hour. But sometimes the pressure compensation or some any turbo key plus this is the same flow rate, but different characteristics. So in the commonly used horticulture crops having large spacing and mango, coconut, citrus, etc., suitable for drip irrigation. There is another kind, it's called, the main thing here in case of online sprinklers, online emitters, is the dripper spacing can be adjusted. So if you go for another crop, just dismantle the dripper and make another hole, and then insert the burp into the lateral. So there is another system called emitter pipe system, that's inline drip system. So yeah, during the dripper is inside the drip tape, and it is fixed inside, and space cannot be adjusted because it's already inside the pipe. Like if you see here, so that this is the drip tape, and then this is the dripper which is inside the drip tape, and so the spacing cannot be adjusted once it is decided. So this is available for different spaces, and based on the crop spacing you can select and buy this, and very effective for row crops like cotton, sugarcane, groundnut, and vegetable and horticulture crops, this one. And then okay, so the next is other forms of irrigation. If you see here, the hand watering, this is very well used in the gardening, nurseries and fruit trees, and then capillary irrigation. So in this case, so air, this is basically there are some wicks, and there is an underground water pipeline which is just beneath the soil root zone. So the air, since the pipe is open to the atmosphere, air will be passed. So the wick basically is going to extract water from the pipe to the soil system. The air will allow to dry this so that I mean the pores will be emptied, and then the water from the pipe can be sucked and pass it onto the soil surface, I mean soil. So that way the air helps. So this is buried pipes or deep surface canals, and this is the root zone by capillary rise basically. So the water will be rise through capillary and water the root zone here. And then so this is the overall comparison of the system. If you see here, so the first column indicates the site and situation factors. For example, what is the soil type, infiltration rate, topography required, crop, and water quality, capital requirement, labor requirement, right. So for different irrigation systems like a basin, border, furrow, sprinkler, drip, so this so what kind of situations, what kind of favorable situations are required. For example, soil, so for basin is loamy to heavy soils, and if you see labor requirement, so high labor requirement is for basin irrigation, for furrow medium, and for drip irrigation low labor requirement. And if you see the efficiencies, so these are the efficiencies, the lines. So it's like subsurface irrigation, you get more efficient 85 to 95% irrigation. So this will tell us the overall comparison among the different irrigation methods we just discussed. And then the other cases left, like energy requirement, skill requirement, whether it causes any diseases to the locals, the operational maintenance. So all these things you can go through it. It's a very helpful slide. And then so the next is irrigation efficiency. If you see, basically irrigation efficiency, the water you are giving to the plant, we should know whether that is efficient or it is excess or it is inadequate. So if you are giving less water to the plant, that means that inadequate, that definitely influence your yield here. So look here, and if the depth is optimal, that means you get a maximum yield. So if the water depth is excess, and your yield is going to decline. So I mean, if you are giving a lot of water, so sometimes the plant is not comfortable with water, and that definitely influence the growth and ultimately the yield. So irrigation water losses could be in case of sprinkler irrigation, spray droplet irrigation, and weed water use. So weeds are going to take water, and evaporation from the soil and furrows. In case of furrow irrigation, the water in the furrows can be evaporated, and then the soil, water from the soil can be evaporated. Leaks in the pipes can cause water loss, seepages and surface runoff, depercolation. See, all these things are going to cause your water losses. So definitely that's going to influence your efficiency. So that's why you see the efficiencies will vary from different irrigation systems. So for example, the whole irrigation system can be looked in this picture. So you will get the water from the canal here to the field. Okay, so this is basically from canal to the field. So let's say the water which is taken from the canal is Vt, that is in meter cube, and then when it is reaching to the field, that is Vf. So how the conveyance, this is called how the system in conveying the canal water to the field, whether that is efficient or not. So that will be decided with EC, that is called the conveyance efficiency. So this is your Vf by Vt, Vf by Vt into 100, so that will give the conveyance efficiency. So that means there is a system which conveys canal water to the field water, and you would like to know whether how much efficient that is. And then once the water reaches the field, and there is a irrigation applicator which takes care of the applying the required amount of water to the field crops. So let's say that that system is that system, and EA is the application efficiency. So the application efficiency what we are thinking is how much water really going down to the root zone. That is more important in our case, irrigation case. So that is your Vs. So here Vf is going in and Vs is going out. So basically your EA is the Vs is volume of water stored in the root zone divided by volume applied. So that will give you the application efficiency. So then in the root zone there is let's say another system which takes your water which is going to the root zone. So for example, so this one VFC minus VA, so this is before irrigation will decide how much water really requires to the root zone. So that is VFC is the volume of water required, the field capacity, and this VA is the actual volume before irrigation, actual volume absorbed before irrigation. Okay. So this difference we need to replenish. So whether this Vs which is going into the root zone can replenish this demand or not. So that this ES represents. So ES here is Vs, which is the finally we were expecting the Vs will go and meet this, but this is the demand. VFC minus VA is the demand, and this is Vs is the supply. So then Vs is the storage efficiency. Okay, and then so then there are water, when you supply water, it splits into, like, one is Vs which is going into the ground, and Vr which is runoff, and Vb some beneficial water and beneficial water. So the Vf is being divided into Vb, Vr and Vs. Vr is the runoff, Vb is the volume of water required for beneficial use. So here Ei is the irrigation efficiency. So that is irrigation efficiency is, so Vb by Vf. So whatever amount of water you supply to the field Vf, so whether it's beneficially used or not, so that is Vb. So that's Vb by Vf into 100. So the mostly this includes your ET plus other beneficial use, like field preparation, other things. So that amount, so that is irrigation efficiency. And EO is the overall efficiency, that EO. So that will be your conveyance efficiency and application efficiencies multiplication. And so EE is the extractable or the effective efficiency, effective irrigation efficiency, if you see. So this is overall irrigation efficiency, and this is mostly used for reuse system, water reuse system. So what about the VR you collected at the end, whether if you use that as reuse or re-irrigate the plant, so then the effective efficiency, that will be overall efficiency plus the fraction of runoff, 1 minus E naught into 100. So this is the effective efficiency. And then the next is, so these slides give an idea on irrigation systems and the potential efficiencies. So the EPA, the LIPA, low energy precise applicator, is 80 to 90% in case of sprinkler irrigation, which is high. In surface irrigation, you get maximum in case of the precision level basins. Micro irrigation case, you can get more. Subsurface drip irrigation is highest. And then the next so the next is the previous things, whatever we see, that responses. So those are engineering aspects basically. So we would like to see the amount of water we apply to the field, how the crop is responding. So these three efficiencies will be related to the yield. So one is the crop water use efficiency. So that is um, so yi is the yield of the irrigated crop and yd is the yield of the equivalent rain-fed crop. So you have irrigated crop and so you have irrigated crop here, right? This is irrigated crop and other one is rain-fed crop. Okay, so this is irrigated and rain-fed crop. Okay, so you have yield I and yield D. So what you are going to do is you are going to see the difference in yields and then the ET I mean of this one and ET of this system. So this difference by this difference will give you the crop water use efficiency. So this is the yield difference and the ET difference. Similarly, irrigation water use efficiency, this is crop water use efficiency, irrigation water use efficiency, we only consider here. So this is the yield difference divided by how much irrigation water really used for this. And then water use efficiency, that is irrigated, I mean yield due to irrigation water divided by effective precipitation, irrigation water and soil water. So this is the total water we used for producing the crop. So this is water use efficiency. So the total water used in growing this crop. Okay, so this needs to be remembered. And then irrigation uniformities. So irrigation uniformities here, there are I mean for a different irrigation method, different uniformities. For example, here for sprinkler irrigation, the Christiansen's uniformity coefficient, so which is defined as Cu is equal to 1 minus xi minus xm by sigma xi into 100. This is sigma, whole sigma. So how do we get the xi's? So suppose there is a sprinkler here. So sprinkler here. So we are going to put the catch cans all around at equal distances. Then we are going to run the system for some time, and then we are going to collect the catch cans and find out the volumes, and that is basically the xi, and xm is the mean of those, and then the rest is the same. So sigma xi is the sum of the volumes of all catch cans. And then for surface irrigation, this is low quarter distribution uniformity. If you see the surface irrigation, so water will be applied here and that will reach here. So at the head end, the water I mean infiltrates much higher than the tail end. So obviously you see there is the water, I mean this is the cross sectional view of the wetting front. So there will be head end, you get higher soil moisture depth, and the wetting front depth is lower in the tail end. So in this situation, so the recommended formula for uniformity is this. So we will take the last 1/4 of the depth of wetting front and then the average depth of wetting front. And then by 100. Okay, and then the next is for drip irrigation, you have this formula emission uniformity for micro irrigation, so which is equal to 1 minus 1.27 into CVM into n power minus half Q mean by Q average. So this is basically in the previous case what we are expecting is for micro this so water fronts will be estimated, because the CU DU concepts are impractical for micro irrigation because the entire field does not wet. So in the other case, the whole field is wet at the end of the irrigation, but in case of micro irrigation. So you would see in the beginning is all the wetting fronts are like bulb shaped. So the uniformity of irrigation is expressed in emission uniformity, so which is given in this formula. So where N is the number of emitters per plant, CVM is the manufacturer's coefficient of uniformity, and Q min is the minimum emitter discharge rate at minimum system pressure. Q average is average emitter discharge rate. Okay. And then, so improved, then after that, so let's I mean we have some since we have some time, so it's improved rice irrigation methods. So the actually with the conventional irrigation methods, so you need to maintain certain amount of water on the ponding, for example 5 to 10 centimeter, which can consume about 50 to 150 centimeter of water in the whole season. So in order to reduce that amount of water, so there are some improved irrigation methods available for the paddy, the rice. The one is alternate wetting and drying. So in this case, alternate wetting and drying, so there will be a perforated pipe installed in the field. So initially the water will be at the ponding water level, then after that it is going to be depleted. We are going to wait this water till reach the 15 centimeter down the soil. So then after that we are going to irrigate it back to 15 centimeter on the surface. So this is the way alternate wetting and drying. So it can save up to 20 to 54% of irrigation water, and reduces 23 to 40% of percolation, and also reduces 10 to 30% of nitrogen loss. No significant yield reduction may be possible in case of alternate wetting and drying with this irrigation pattern. So this is very good system compared to the conventional system. The other system is the system of rice intensification. So the main difference here is we are going to increase the plant to plant spacing. So mostly here is like 25 centimeter by 25 centimeter, and the seedlings are like 10 to 8 days seedlings, and and only single hill we are going to practice, sorry, single seedling per hill we are going to practice in this case, in SRA case. So this practice can save, and also the field is nearly saturated. So every time we are going to pond the soil, just to near saturation is practiced. It can save up to 22 to 39% and increases the grain yield up to 8 tons per hectare, and reduces 23 to 38% of percolation. And the last one is the bund plugging. So in case of bund plugging, the practice the Patil et al. 2011. So what they did was the initial basically the bunds have the macropores. So there is a lot of the water can pass through the macropores, and that will be the enormous losses. So in case of bund plugging, so you take the existing bunds out and they compact the soil like a puddle soil, then rebuild, put the bunds back into the place. So that practice can save up to 22 to 50% irrigation water, and it can reduce the percolation up to 50%, and no significant reduction in the yield was observed. So there are some improved irrigation methods here. So with this we are going to stop here, and then the next we are going to talk about other other topics in this series. Thank you so much.